So, as you may be aware, there are different types of operating systems for various different uses. Now, the ones you'll be most familiar with are probably Windows on your laptop or your computer, and a mobile operating system, probably much like iOS or Android. Now, operating systems are are quite varied, and they obviously account for different hardware. So your operating system is generally written for a particular type of hardware. Now, obviously, operating systems like Windows and Linux are written for a broad base of desktop hardware, so laptops and desktop computers. Mac OS, or OS X as it was previously called, was particularly for MacBooks, although it is possible to run it on a different laptop or desktop with some difficulty. But those are generally cater for the laptops and desktop computers, whereas your mobile operating systems are written for a very specific piece of hardware. So they are quite tailored to the particular device that they're running on. Even your Android operating system will need to be tailored for each particular smartphone, although the core of the operating system is essentially the same. We do, of course, know that there is open source or open architecture kind of software which is freely available, and you can change the source code of that. And then there's also proprietary software, of which you will know that Linux and Android, for instance, are open architecture or open source, whereas Windows and macOS and iOS are closed architectures or proprietary, as they're sometimes called. What follows is generally an explanation of how we can go about running different operating systems on the same hardware. Now, those of you that use Mac computers will know that there are programs like VMware and Wine and Parallels, which essentially allow you to run Windows on a Mac. In fact, Parallels and VMware allow you to run Linux on a Mac if you so wish as well. And there are different ways. So one of them is essentially what we call virtualization. So you'll install a piece of software on your existing hardware in your existing operating system, which will allow you to run a different operating system. So in my case over here, I have Parallels installed, and I can show you over here, even though this is a Macintosh computer, here is Windows running inside of an application, essentially inside of my Macintosh computer. So I can install Windows 10 here. I actually also have Windows 7 also installed on the same computer, which will come up in a different window if I choose to open it. But this is fully functional Windows, which I can then use in order to perform tasks on a Macintosh which are exclusive to Windows. So this is essentially a type of well, it is virtualization, which is one particular way that you can run a different operating system on top of your existing one. There's also something called dual booting, and dual booting is essentially when you take your hard drive, your physical hard drive, and you partition it into two parts, and you install one operating system on one part and another operating system on another part. What you will need to do then is to, when you reboot your computer, you'll be given an option. Do you want to run Windows or do you want to run Linux? Once you boot into that operating system, you can only use that operating system. And that's called dual booting, so that you can boot into one of two or three operating systems. But once you're in that operating system, you have to use that operating system. The advantage of that is they do run quicker. Running an operating system in a virtualized environment, like I just showed you, is more resource intensive, and you can have some problems with certain drivers or devices or things like that. So, but the advantage is that of virtualization is that you don't need to reboot in order to use another operating system. Whereas dual booting, you do have to do that. So those are the two ways that you can run different operating systems on the same piece of hardware. The last section here is programming languages. Now you might be wondering why programming languages are included in a chapter on operating system. Well, programming languages are essentially seen as system software. They are not used by your typical end user, but they're known as system software. So there are various kinds, and the first one that is covered here is high-level languages. Now, high-level languages are the programming languages that you have been exposed to. So Java or Small Basic or whatever the case may be. And they're pretty much human readable. Okay, so you've got commands like while loops and if statements and assignments and string manipulation. They are high-level languages. And that is where most programming takes place. It's a high level of abstraction, and 99% of all your programming will take place in a high-level language. However, more importantly, there is something called a low-level language. Now, low-level language, essentially, every single command that you see in a low-level language can be translated into an instruction that the CPU can understand. So assembly is an example of a low-level language, and this is the piece of code which executes the Fibonacci sequence exactly the same as you see it up there. But each of those lines of code can be translated into an instruction which the CPU can understand. So each of those that can be translated into a binary or hexadecimal instruction which can be given directly to the CPU and executed. Low-level languages are very difficult to code in and to read in, but they're very fast and they're very efficient. So you don't need to rely on kind of your high-level language implementation in order to get efficiency out of there. Also for hardware drivers and things which work with low-level hardware, low-level languages are quite useful and almost a necessity. So the reason I'm telling you about low-level languages is because there's a piece of software which allows us to convert high-level language to low-level language. Because remember, your CPU can only run low-level languages. It only understands machine code. It doesn't understand Java. So what we need is something called an interpreter or a compiler. Now, interpreters and compilers are slightly different, but both of them essentially translate high-level languages into machine code. So they'll take the machine code and they'll translate it into a form that the CPU can understand. Now, the difference between them is interpreters will execute one line of code at a time. So in an interpreted language, for instance like PHP, it'll execute one line of code, it'll compile, well, compiles maybe a confusing word, but it'll take the first line of code, translate that into machine language and execute it. It'll then take the second line of code, translate that into machine language, then execute it. Third line of code, translate that into machine language, and then execute it. And it will only really crash when it finds an error. So it doesn't look for errors at first. It'll only really come across an error, even syntax errors. So if you leave out a semicolon or a bracket in PHP, it'll only recognize that when your code is running and at no time before that. Compilers, on the other hand, are run through the entire program and translate it before attempting to run it. So it'll take all of your high-level code, like in Java, it'll attempt to translate that all into machine language, and then it will run the machine language. And that is why if you try and run a Java program that has a syntax error, it's not going to run. Your NetBeans is going to tell you have a syntax error. That is because it has attempted to go through the entire high-level language, all the Java code, and try and translate that into machine code before running it. Now, the disadvantage of compilers is that it compiles to a particular platform. So if you take a typical language like Delphi or C# and you compile it, it'll be compiled for that machine. It'll be compiled for Windows. Or if you're on a Mac, it'll be compiled for Mac. Or if you're running Xcode on a Mac and you compile it, that will be compiled for Mac. That machine code will be specific to the operating system you compiled it on. So code that you compile on a Windows machine won't run on Mac or Linux. You will have to compile it for Mac and for Linux and for Windows separately. Interpreters are a bit more flexible. but you do lose speed. So they can be slightly slower because each line needs to be interpreted one line at a time and then executed. Compiled languages are much faster. They are compiled to machine code and they're ready to run at any given time. So compilers, advantage, they run faster. Disadvantage, they need to be compiled for every platform. Interpreters, advantage, they can be run on any platform without having to recompile or reinterpret. Disadvantage, they are a bit slower because of the overhead required to do that. Now, and you can see we've got a bit of a diagram here. So the source code essentially gets in an interpreter, gets translated one line at a time and sent to a processor, and the source code for a compiler all gets compiled to machine code, and that is run. Now, Java gets around this whole idea of having to compile once for each platform in a very interesting way, and it's been quite revolutionary. What it does is Java compiles, it does use a compiler because you'll notice you get syntax errors before your program runs, etc., etc. But what it does is it essentially compiles the source code to run on a virtual machine. Okay, a computer, a kind of an operating system or computer that is virtual, so not the one you're running on, and that is called the Java virtual machine. And the Java virtual machine is you could think of it as a mini operating system which understands the result of a compiled Java program. So you will see it compiles to something called Java bytecode, and that's if you ever see your .class files in your source code, that is compiled Java code, and it compiles it to bytecode. The virtual machine is then an interpreter which can execute that bytecode on any machine. So you'll get your Java virtual machine for Windows, Java virtual machine for Linux, Java virtual machine for Mac, Java virtual machine for mobile operating systems. And the advantage of that is that as long as you have the Java virtual machine installed, you can run any code compiled by Java. So Java compiles to this intermediate virtual machine. So it compiles to bytecode, and that bytecode is understandable by any Java virtual machine, regardless of what platform it's installed on. So that's incredibly useful because it essentially compiles your code to machine code. That machine code isn't specific to Windows or Mac or Linux, it's specific to the Java virtual machine. The Java virtual machine on any of those operating systems can interpret any bytecode that was compiled by a Java compiler. So that's the way that Java gets around that. And that really concludes this chapter on operating systems and system software.